Recording. Okay. Okay, so today we have Chris Flett, who is going to tell us about exclusive in jet side production at next to in order. So, well, Chris Flett is an expert in small X physics and jet side production, and he did his PhD in Liverpool, and now he's doing his postdoc in Jyvaskyla. Well, okay, the room is yours. So you can start.
Okay, so thank you very much for this kind invitation for the introduction to talk at your seminar series. So indeed, what I'll be talking about will be exclusive JSI photoproduction in PP and lead-lead UPC collisions to next leading order in PQCD. So the lead-lead work is in collaboration with the people on the left here from Jyvaskyla, and then the PP work is in collaboration with people on the right here. And here I use a slightly refined framework, as I'll soon tell you about. So here's just a little outline of my talk. So I'll start with some introductory remarks about the setup and give a general motivation. In part one of my talk, I'll discuss exclusive JSI photoproduction conventional collinear factorization at next leading order. So here I'll restrict the discussion to lead-lead UPCs. And so this talk will be based on a recent preprint with the archive number given here by this group of people in Jyvaskyla. So here I'll discuss the scale dependence at next leading order for this observable, show the decomposition of the leading order, next leading order amplitudes into the real and imaginary parts, and then show the interplay of the quark and gluon next leading order amplitudes, and show how this gives rise to actually some unexpected results. And then I'll conclude this first part with a comparison to data. So hopefully that'll take around half my talk time. In part two, I'll then discuss exclusive JSI photoproduction and a tamed collinear factorization approach at next leading order. So this will be for Pb UPCs and will be based on these papers here with the other group. And here I'll really emphasize or explain exactly what I mean by a tamed collinear factorization, which basically amounts to some explicit GPD modeling, some low X resummation, as well as implementation of a crucial Q0 subtraction. So with this sort of new and improved theory framework, I'll then compare to data, and then show how this motivates and ultimately allows us to extract a low X and low scale gluon PDF. So that's essentially the outline of my talk. So here is just a motivation slide more than anything else. So of course, inclusive processes such as DIS or deep inelastic scattering do not well constrain the small X domain of PDFs. So we can see that in these plots here in the corner here, which show various error bands from various global filter groups. So here is NMPDF, MMHT, which is now MSHT, and CT collaborations at some fixed low scale close to the input scale. And we can see here that as X goes to 0 here, the error bands that they obtain for their gluon distributions get very, very large, arguably consistent with unphysical decreasing gluons, and of course with 0 itself. And of course, the reason for that is that in this region of the phase space, there are no data support used in a global PDF analysis. Of course, also for larger X, we also have quite a sizable uncertainty. So it's not visible on this log linear display, but if we take ratios of the different sets relative to each other, we can see that for X greater than about 0.1 and into the valence regime, we also have quite a large uncertainty. And of course, that has consequences for quark-PDF flavor separation and BSM searches. But in this talk, I'll only discuss the small X domain, essentially the errors at small X and large X effectively decouple. So the question I want to ask is, what can we do about this small X region? So of course, it turns out there are certain exclusive observables that basically provide a handle on this small X regime and sort of act as more sensitive probes of exactly this region. So in particular, in 1993, Riskin showed that the leading log approximation for exclusive JSI production was directly proportional to the square of the gluon PDF, as his famous formula here shows. This is for gamma star P going to JSI P. So because it shows up as a square here, it means that through this process, we're sensitive not only to the gluon PDF, but more importantly to the small X domain of it. So that's sort of exactly why we're interested in the exclusive JSI production. So yeah, just to emphasize that the inclusive process is one where we have an inclusive cut over all final state particles. And all we're measuring is sort of the energy or scattering angle of this final state lepton. And in the exclusive mode, we have then a well-defined final state, in this case, the vector meson, which is then separated by a characteristic large rapidity gap theta here with respect to this final outgoing proton momentum. So the underlying question we want to keep in the back of our minds is, can we use this exclusive JSI data to really constrain the gluon PDF in this far left of this plot here, an unconstrained regime? So that's just the motivation. So now I'll discuss part one, which will be for the exclusive JSI production conventional collinear factorization at NLO. So here's just our general setup and assumptions. So here I'll discuss lead-lead UPC or ultraperipheral collisions in the conventional collinear factorization approach. So ultraperipheral because there's no nuclear overlap, and these two lead nuclei here will interact electromagnetically. So these are the diagrams that we should have in mind. So they're Pomeron diagrams where a photon comes in, fluctuates into a CC bar heavy quark pair, and then goes on to form the J psi after imposition of projectors in color and spin space, which is sort of represented by this gray blob there. So basically that's a bunch of Kronecker deltas and a VEV of a dimension 6 operator that sort of encodes all the non-perturbative formation dynamics for the outgoing J psi. We're however interested in non-relativistic formation for the J psi. Basically means to say we assume a zeroth order term in the expansion of the relativistic velocity of these outgoing quarks. Just means to say we assume they're equal momentum parallel outgoing constituents. There are corrections to that, which was studied by Hoodboy in the 1990s. And he basically showed that the first relativistic correction amounted to of the order of a few percent. So it's sort of beyond the accuracy that we require. These two gluons here are color correlated. So as we have a color singlet exchange, so these will be color correlated so as to ensure no color breakup of this lead nucleus between the initial and the final state. And we also have the usual separation between the different degrees of freedom in the process. So between the hard sector labeled by C here, which amounts to computation of the hard matrix element for this gamma glue going to two outgoing quarks to next leading order of perturbation theory. And then here we have the soft sector labeled by F here, which are, in this case, the GPDs or generalized parton distributions. So we're susceptible to GPDs rather than the forward usual PDFs because of the presence of the skewness parameter psi here in the parton momentum fractions. And I'll say a few more words about that in the next part of my talk. So here is just our statement of factorization spelled out explicitly at the bottom of this slide here. So here it's for the gluon sector, and here is for the quark sector. So these W plus and W minus diagrams here basically arise in ultraperipheral description of the gamma P to J psi P subprocess. And they basically arise because of the lack of tagging at the experimental machines. So we cannot be sure which lead nucleus this initiating photon came from. So we have an extent of quantum mechanical interference between these two configurations here. So here are these configurations spelled out explicitly on the right-hand side of this equation here for W plus and W minus. So for a given rapidity y of the vector meson, we have photons of energy k plus and k minus given by this expression here, and they correspond to configurations W plus and W minus. So pictorially, what we should have in mind here is that a W plus configuration corresponds to this diagram here, where the vector meson, in this case the J psi, goes in a direction of the photon, which came from the lead nucleus. And for the W minus, it's then the J psi going in the opposite direction to the photon, which came from the lead nucleus. So that's it pictorially. And in terms of equations, we have these two contributions here, so W plus and W minus. And on the left-hand side, we have d sigma by dy for the AA to AVA process. So in this talk, this A will just be lead. And the left-hand side is what the experimentalists measure. And then we just decompose that into these two contributions here, W plus and W minus. So this dN by dk here is the Weizsäcker-Williams photon flux. So here we actually explicitly perform the integral over the whole impact parameter plane and also include a survival factor, which accounts for the probability of having no additional hadronic interactions or indeed interactions involving the spectator partons in the lead nucleus. So that basically accounts for, in principle, factorization breaking corrections, and here a subset of those, this Eikenol contribution as well as enhanced contribution shown here. So that all goes into the analysis. These sigmas here, of course, the hard scattering partonic cross sections, just given by multiplication of the d sigma by dt evaluated at the zero momentum transfer here, multiplied by the explicit integration of the nuclear form factor. So here we use the Wood-Saxon distribution and then just perform this integral explicitly here. So this d sigma by dt here is proportional to the amplitude squared, modulus of the amplitude squared. So I give this on the previous slide here. So here the input is the coefficient functions. So for photoproduction relevant here, we take them from this paper here, and for electroproduction, which would then be relevant for like EIC kinematics, that were then computed in these more recent papers here. And then we convolute those coefficient functions with the GPDs, and in this baseline approach, we take the GPDs in our forward limit, and then sort of just perform this convolution, and then that gives us our amplitude. So then we then have all the pieces to then make the theoretical predictions for d sigma by dy, which is what I'll show now in the following slides. So here I start with the main presentation of the result. So here is the scale dependence at next leading order. So this is a plot of d sigma by dy for lead going to lead plus j psi lead versus y rapidity. And here I've shown it for the nucleon center mass energy of 2.76 TeV using EPPS 16 partons at next leading order. And here I've fixed the factorisation scale equal to the renormalization scale and varied it from this lower curve here, which is set equal to the mass of the charm, all the way up to this upper curve here, which is twice the mass of the charm, or in our QCD approach is then equal to the mass of the j psi. So as I make this variation, we can see that actually there's a large area swept out, and we can certainly say that this observable exhibits a large dependence with respect to variations of the scale. And this is also the case at the run 2, nucleon center mass energy of 5.02 TeV, as shown in this lower panel here. So this central solid red line here is what we've dubbed optimal scale, in the sense that we can sort of well reproduce the data at run 1 and run 2 collision energies. So the value we find is around 2.37 GeV. Of course, the explicit value there is susceptible to change as we sort of incorporate more GPD modeling into the game, but all we want to emphasize here is that it is possible to find a scale that well reproduces the data at both collision energies. So yeah, just to emphasize, of course, that there is a large scale variation here, and of course that's not new. It's not a new result for this observable. It was first discussed in this paper here back in 2004, when the presentation of the next leading order coefficient functions were first given. So it's a well-established result for this exclusive JSI photoproduction and collinear factorisation. I'll say a few more words about what this large scale dependence means when I come to look at the outlook for this observable. So here I just want to break the amplitude up into a few different ways. So here is just showing just the decomposition of the leading order, next leading order amplitudes into their real and imaginary parts. So the top panel is for leading order, and the bottom panel is next leading order. And this is generated at our optimal scale at the run 2 center mass energy of 5.02 TeV. So we can see in the top panel here that the imaginary part of the amplitude dominates the result over the whole rapidity range. So that's this orange curve here, and the blue curve is the total result. So that's sort of in line with the expectation of Reggie theory, where the real part is sort of continuously subdominant to the imaginary part, especially at high energies. However, at next leading order, the situation looks a lot different. And we can see here that around mid rapidity, the real part contribution actually contributes around 25% to the total result. So the real part is no longer negligible. And actually there's a region around y equal to plus or minus 4, where the real part actually is larger than the imaginary part. And again, these statements here are qualitatively reflected in this original paper by Ivanov and others in 2004, where the presentation of the next leading order coefficient functions were first given. So now I just want to break up the result into a slightly different way. So this is just showing the interplay of the quark and gluon at next leading order. So again, it's a plot of d sigma by dy versus y, here generated at 5.02 TeV using EPPS16 partons at next leading order. And this time I fixed the factorisation and renormalization scale equal to our optimal scale of 2.37 GeV. So that's this blue curve here, which I showed in the previous slides. And here I've just decomposed it into only quarks, only gluons, and their interference, this red curve here. So this plot may actually come across as quite striking because, of course, at leading order, we only have gluons in the game. And then when we proceed to next leading order, when quarks come into the picture, we then have this sort of complicated mix of contributions. So I think what's perhaps most noteworthy is the fact that around mid-rapidity, we have a quark dominance. So that's shown by this green line here. And that actually reflects the poor perturbative convergence of this observable, in the sense that the leading order, next leading order gluon amplitudes have opposite signs. So it so happens that around mid-rapidity, there's a large extent of cancellation, which then provides for the quark dominance around y equal to 0 here. So actually, in absolute terms, the leading order, next leading order gluon amplitudes are larger than the quark amplitude, but in the construction of the amplitude at next leading order, it so happens that they sort of conspire to cancel, and that leads to the quark dominance at mid-rapidity here. I think what's also worthy here is the appearance of these side bumps here, about y equal to plus or minus 4 here. I won't say too much about them, but essentially they arise from a detailed interplay of the photoproduction cross-sections, photon flux form factors, and the W+ and W- components. But it's also interesting to note that these side bumps actually arise also in the ρ0 photoproduction and lead UPCs at next leading order. So now I just want to show similar plots as in the previous slide, but now with the PDF errors on top. So here both plots are at next leading order. For the run 1 collision energy 2.76 TeV, and the bottom is for 5.02 TeV, the run 2 energy. So this solid blue line here in the dash red are the central predictions obtained using EPPS16 and NCTEC15 parton sets, next leading order. And this shaded blue band and orange band here are then the nuclear PDF uncertainties. So we can see here that both collision energies, they nicely encompass the available data that we have from ALICE and CMS, and also LHCb at in this lower panel here. So this shaded green background here is in the band we get if we include the free proton PDF uncertainties, and we can see here that they're very large, and actually we've checked that this is dominated by a single error set where the small x gluon is rising rather rapidly. So I also want to emphasize that for rapidities here at the run 2 nucleon center mass energy, we also have this tension between the run 2 ALICE and LHCb data. It's been discussed many times, but just to sort of emphasize it there. So it'll be interesting to see what the reconciliation of these data points will be. Okay, so now I will summarize the part 1 of my talk. So here I've discussed the very first implementation of next leading order collinear factorization to exclusive photoproduction of Jyvaskyla and lead UPCs. So I mentioned a few noteworthy features, which is that there's a large scale dependence exhibited by this observable, and also that the quarks dominate at mid-rapidity and next leading order. And one might not expect that, given that the process at the leading order is completely driven by the gluons. So if you sort of recall, the main motivation of studying exclusive Jyvaskyla photoproduction is sort of the sharp sensitivity to the gluon PDF, and sort of the aim would be to ultimately use the exclusive Jyvaskyla data in a global PDF analysis to really constrain the low X gluon PDF. So these two statements here really sort of hinder that approach, or ideology, if you like. So of course, what I want to emphasize is what I've discussed in part 1 of this talk is the approach within the conventional collinear factorization. So a lot of the statements I've made sort of reflect back to this original paper by Ivanov and others in 2004, where these things were first discussed. So a lot of progress has been made since then. And what I want to discuss in the next part of my talk is exclusive Jyvaskyla production and attained collinear factorization. So this basically amounts to some low X resummation and implementation of a crucial low Q0 subtraction. So it was shown in these papers here that by putting this into the framework, we then get a mild scale dependence, and also that the quark contribution is in basically zeroed. And I'll show this in the subsequent plots in part 2. So we can sort of compare and contrast these two bullets here in the conventional approach and also in the refined approach. So just to be explicit, the refined framework then amounts to a tamed collinear factorization where we have these two things incorporated. And then the Jyvaskyla transform is a means to relate the PDF to the GPD, and also again NRQCD for the CC bar to JSI transition vertex, which is also what we use in the conventional approach. So yeah, so it's shown in these papers here that this framework then allowed for a meaningful comparison of the data, and therefore that then motivated and ultimately allowed us to extract a low X and low scale gluon PDF. So with regards to the lead-lead context, what we'd want to do moving forward is to really sort of move this refined framework also into the lead-lead territory and see how it looks there. So we've we've put this framework into proton lead, and this is basically a paper that we have in preparation at the moment. But the next step would then be to sort of move this forward into the lead-lead as well. Okay, so now I'll proceed with part 2 of my talk. So here I'll discuss the exclusive JSI photoproduction and a tamed collinear factorization and excluding order as I've introduced. So this is mainly just a introduction to GPDs and how we extract them at low X using what's called the Jyvaskyla transform. So GPDs generalized PDFs in the sense that the outgoing and incoming partons can carry different momentum fractions. So if you look at this picture here, it's a plot of the scenario. So here we have psi 0 kept p as amplitude to pluck out a parton at space-time location 0, and then propagates to y through this path-ordered Wilson line, where it's then subsequently destroyed by Bra-P prime sar by y. So this matrix element here, together with an explicit integration over the coordinate y here, then defines sort of the coordinate space GPD. So because of the presence of the skewing parameter psi here, means that we have a p primed rather than p in the final state. If we send the psi parameter to 0 here, the momentum fractions carried by each of these active partons is then x. This p prime goes to p, and then we sort of map back onto the familiar conventional collinear PDFs. So the statement of Jyvaskyla was that really there is a relation between the GPDs and the PDFs at small x, assuming sort of certain conditions surrounding analyticity are upheld in the complex plane. So broadly, the idea was that the conformal moments of GPDs really do map onto the mellow moments of PDFs, with the caveat this is true up to corrections of order psi squared at leading order, and then order psi at next leading order. So I put the Jyvaskyla transform in the next slide just to sort of flash the transform, but essentially it amounts to sort of a slowly converging double integral transform that's actually quite costly computationally. There are analytic approximations to the Jyvaskyla transform in the literature, but what we do anyway is to really push ahead and use the full transform. So what we do is to construct GPD grids in a 3-dimensional parameter space spanned by x, psi over x, and the scale q squared. And then we take the forward PDF grids from the LHC PDF6 interface and then sort of just cast them into the Jyvaskyla transform. And that gives us a set of low X GPDs to work with. So there's actually a region in a parameter space where the Jyvaskyla transform is not valid, and that corresponds to this region here between -1 and 0 in this Y plane in this original paper by Ivanov and others. However, in this region, the imaginary part of the coefficient function, which is what we use for the hard sector in this approach, is identically 0. So that allows us to perform the full stretch of the convolution from -1 to 1 that I showed in the amplitude formula in the last part of my talk. So here's just flashing Jyvaskyla transform just so you get an idea of what it looks like. So here I've shown it for the twist to parton helicity conserving quark and gluon GPDs, and here we can see explicitly the susceptibility to the forward PDFs through this derivative factor here. And then we have this double integral here, which basically arises from the transformation from the moment space to coordinate space. And then we have the imaginary part of this integral here, which then sort of provides for the explicit convergence of this kernel, and y of s is given by this expression here. So I'll put a few more slides about the explicit derivation of this in the backup if there's any questions about it. That basically just a few points about the original derivation from what Jyvaskyla presented in his original paper in 1999. So yes, now I just want to push ahead and talk about the process in this refined framework. But first, another quick slide about things in the conventional approach. So in the conventional approach of collinear factorization at next leading order MS bar scheme, the next leading order correction has some unsettling features, such as the next leading order correction being larger than the leading order one and of opposite sign. And moreover, there's a strong dependence with respect to scale variations, as I've discussed in part 1 of my talk at the cross-section level for the lead-lead context. So here is a plot of the imaginary part of the amplitude scaled by W squared versus W here, which is the gamma P center mass energy. And here points A and B are nicely reflected in this plot here. So here I've convoluted the known MS bar coefficient functions, which are known in this paper here by Ivanov and others in 2004, and then with Naratim in 2014. And then they were recomputed in a different framework by Stephen Jones in his PhD thesis at Liverpool in 2014. So here I've convoluted the known MS bar coefficient functions with a known global Fitter group. So this plot is quite old, but here it's for CTEC 6.6, and the message doesn't change. It just reflects these two statements here. We have a large scale variation, and at the leading order and next leading order, corrections of opposite signs. So here we vary the factorization scale simultaneously, the normalization scale by a factor of 2 here, and then by a factor of 4. And we can see the large scale variation that I showed in part 1 of my talk, but now at the amplitude level. So of course, what we want to ask ourselves next is, can we do better? And the answer is yes, we can. This is all before the business of resummation, where we start to consider logs of 1 over psi, which of course are large because we're in the small psi, small x domain. So yeah, just to emphasize, this is how things look like in the conventional picture. So the procedure we want to adopt is the usual procedure of scale fixing. So we consider logarithms of this form here. So it's logs of 1 over psi that come equipped with a log of mu f over mc at each order and alpha s. So it's a form of double logarithmic form like that. So if you look into the high energy asymptotics of the next leading order correction, we can see that the next leading order result actually becomes directly proportional to a logarithm of this form here. So it's sort of highly suggestive that by setting the factorization scale equal to the mass of the heavy quark, mass of the charm, then we sort of nullify that high energy term completely and also simultaneously resum this class of large double logarithms. So this setting of a scale, of course, amounts to shifting of terms between orders. So we shift terms from the next leading order contribution into the leading order PDF. This then leaves behind a remnant next leading order coefficient function at mu capital F. And then there's a residual smaller mu small f dependence residing in the next leading order GPD. So those words there are basically just summarized in this equation here. So this mu capital F dependence will cancel between these two contributions here. And that then leaves behind a residual mu small f dependence residing on the left-hand side here. So in principle, this equation can be iterated to higher orders, but this is a statement to next leading order. So if we put this double logarithmic resummation into the picture, this is what we get. So this is the same plot as I showed in the previous slide, but now we fix the factorization scale equal to the mass of the charm scale squared. So that's 2.4 Jyv squared. And here we make variations with respect to this residual factorization scale, this mu f here. So here by a factor of 2 and here by a factor of 4. And actually, we can see that the picture doesn't look too much different. There is still a large scale variation, and the leading order result has the opposite sign to the next leading order one. And so there's still hints of a poor perturbative convergence in the game there. So at this point, what we want to do is to really look for another sizable correction that can reduce the variations further. And that's where this implementation of a Q-naught cut comes into play. So yeah, just to emphasize again, this is double logarithmic resummed, this picture here. So yeah, so now I'll discuss the Q-naught subtraction. So this was first discussed in this paper here quite a number of years ago now. And basically it's an exercise to avoid a double counting. So what we want to do is to subtract from the D-Glop evolution the contribution of scales L squared less than Q naught squared. So L here is a loop momentum circulating in this diagram here, and Q naught here is input scale of the PDF. So we want to subtract that contribution from the next leading order MS bar coefficient functions. Otherwise, we sort of, strictly speaking, double count. We put the same contribution to the hard sector and to the soft sector. The reason why this subtraction is so shaky with our numerics is because formally this subtraction amounts to a power correction of this form here. So it's order Q naught squared over the typical factorization scale squared. For exclusive J psi photoproduction, factorization scales around the order mass of the charm, mass of the J psi. And so, and of course, numerically what we do here is set to equal to, exactly numerically equal to the mass of the charm, because that resums the large logs at high energy. And so this correction is then sizable for this process, is of order 1. So this subtraction is actually a ubiquitous or common feature of MS bar calculations, but more often than not is actually typically power suppressed. So for example, at Higgs production, where the typical factorization scale is then of the order of the mass of the Higgs, then this correction is then essentially negligible and there's no need to worry about it. But for low scale processes, such as exclusive J psi photoproduction, this correction is then of order 1 and crucial. And of course, we can see that from this plot here. So here we have the Q naught subtraction in the game, as well as a double logarithmic pre-summation, just by fixing the factorization scale here, mu capital F. And we can see here that the scale variations are a lot more mild, and that the leading order, next leading order results have the same sign. So we can actually finally say that we now have a prediction that is reliable and on a much firmer ground with regards to perturbative stability. So with this sort of new and improved theory result, what we want to do next is really compare to the data that we have for exclusive J psi production from HERA and LHCb. So yes, just to say, this is the Q naught subtracted and double logarithmic resummed plot, just shown there. Oh yes, so before I start showing plots at the cross-section level, here's just the corresponding plot of the interplay of quark and gluons at next leading order in this refined framework. So this is the picture after the Q naught subtraction. So this is the plot of the imaginary part of the amplitude scaled by W squared versus W, generated using CT14 partons at scale Q naught equal to mu capital F equal to MC. And again, just to emphasize, this mu F equal to MC resums a large log. So that's why we choose this. That's the motivation for choosing this value here. So yes, we can see here that over the large range of W here, so this is the range accessible to the current LHC data, we can see that the quark contribution is actually essentially just zeroed here. Well, the driving force of the process, again at next leading order, is the gluon, as this plot here shows. And actually this can be well understood from the sort of the basics of deglap. So we just look at this plot on the right-hand side here. This shows a quark next leading order contribution, Feynman diagram. And we can see here that the quark contribution is always separated from the hard scattering by at least one step of deglap evolution. So it's always the gluons that enter this hard scattering. So of course, if you recall the sort of the strong ordering constraint and deglap evolution with the scales, after we impose the Q naught subtraction, we basically just subtract off the low scale contribution and sort of just hide it into these input PDFs. So then we treat the quarks like as a phenomenological input, and that basically just comes across as like a zeroing and for the quark contribution in this plot. So yeah, just to emphasize that after this Q naught subtraction, the quarks are basically playing no role at all, and the process is again gluon driven, like at leading order. Okay, so now I just want to finally show some plots at the cross-section level. So the plots on the previous slides have all been at the amplitude level, and in particular for the imaginary part of the amplitude. However, we can still restore the real part, which is what we do by evaluating this Reggie dispersive factor here. So this is just computing this derivative factor here numerically, bin by bin, and W. So that goes into these plots here. So this is a plot of the cross-section for gamma P to J psi P versus W. And here are shown predictions for the 3 global PDF sets. So these plots are a bit old now in these papers here, but here I've shown it for MMHT14, NMPDF 3.0, and CT14. So these solid central curves here correspond to the numerics where Q0 is equal to mu f equal to mc, and with mu f squared and mu r squared equal to mc squared. Well, these dashed variation curves here then correspond to mu f squared and mu r squared equal to 2 mc squared. So we can see in these plots here that we have quite a strong scale stability observed in the LHCb regime. Well, in the HERA regime, it's the sort of central solid lines that better agree with the data here. So we can see that the central solid lines for NMPDF 3.0 and CT14 are basically in agreement up to a few units of 10 to minus 4. And then for smaller x or larger w, the predictions based on MMHT14 and NMPDF 3.0 sort of rise sharply. So there's a steep growth here, while the growth displayed by CT14 is then more modest, as this plot here shows. So then we have this sort of diversity in prediction coming into play here. And of course, it's worth emphasizing that in the far right of this plot, just to emphasize a disclaimer, that of course, we're convoluting with the partons in a regime where they're obtained without any data support. So this large diversity in prediction here then sort of tends to an important message that we want to convey to the global PDF analysis groups. And I'll come back onto that in the next slide. But of course, the hope is that where the PDFs are better constrained, around 10 to minus 3 here, the hope is that the data here lie comfortably within the 1 sigma error bands of the PDFs propagated through to the cross-section level in our framework. And on the next slide, I'll show that is indeed the case. So here I've shown that explicitly for NMPDF 3.0, so just this band here. So we can see here that the data lie comfortably within the 1 sigma error bands of the PDFs propagated through to the cross-section level. And then for smaller x or larger w, this band then sort of just opens up and encapsulates the large W data here. So this large band here, of course, just comes from the large gluon PDF uncertainty that I showed in the first slide. So here's a few statements about the error budgets that we can make, which is that the errors due to the parameter variations in the global fits, so this purple hue here, is so much greater than the experimental uncertainty, just these error bars here, and also the scale variations in the theoretical result, which, as I've explained in part 2 of this talk, in this refined framework, they're now under control. So these statements here then really support the claim that the exclusive data are really now in a position to readily improve the global PDF analysis. So I think the advantage of this plot here, it sort of emphasizes the level of discrepancy that we have between the different global PDF sets. While this plot here sort of emphasizes a level of uncertainty within a given PDF group alone. So I think these two things combined really do support the claim that the exclusive data really are now in a position to readily improve the global PDF analysis. So just to emphasize, the exclusive LHCb data will constrain the small x behavior, whilst the exclusive HERA data, so these ones at lower W here, will then improve the determination of partons in a regime where we already have a multitude, lots of data already from diffractive DIS experiments. So that's the hope indeed. Okay, so this is now my final slide. So now I just want to end by showing two approaches that we've used to extract a low X and low scale gluon PDF using this exclusive JSI data. So on the left here, we do a fitting exercise. So we fit a low X gluon PDF ansatz to the data and then match onto the global partons at a much larger X. So here are our various chi-square per degrees of freedom, best fit parameters, and their 1 sigma standard deviation shown here. In approach 2, we then do a Bayesian reweight of current global PDF analysis. So here I've shown it for NMPDF 3.0. So that's on the right here, and that corresponds to this blue hatched band. So of course, in both approaches, the only constraining power at small x comes from this exclusive JSI data. So that's where the predictions overlap here. And then at the larger X, we have this mismatch, which is basically alluded to the fact that, of course, in the global PDF analysis, they have a lot more data at 10 to minus 3. So this sort of provides for a more streamlined PDF set, which then provides for this mismatch at 10 to minus 3. But anyway, it's nice that in the low X regime that our reweight prediction is backed up by an actual fit to the data. The only point of discussion really is the fact that the extracted gluon that we have, which is this one here heading upwards for smaller x, is sort of going in opposite direction to the one obtained from the Bayesian reweighting of the inclusive D meson data, which is this grey band here, which goes down for smaller x. And it's a discussion point. I'll put a few more slides in the backup slides if anybody has any questions about why we think that there might be sort of a inconsistency with experimental measurement of the inclusive Ds. So that's for the discussion if there's any questions. Okay, so now I'll just summarize. So I've started off by talking about the conventional MS bar next to the order collinear factorization picture, and showed that that's ultimately unreliable and unstable due to this large scale variations. So this was discussed in part 1 in the context of lead-lead. And then in part 2, I've then showed how we can sort of systematically tame the conventional approach via implementation of a Q0 subtraction and resummation of large logarithmic corrections that then collectively reduce these wild scale variations seen in the conventional approach. And then with this sort of new and improved theory result, we can then sensibly produce predictions at the cross-section level. And I showed too that they have good stability and that the central values are in agreement with the data within the 1 sigma error bands. So also emphasizing that there is this large difference of the central predictions based on the global PDFs and the LHCb regime. But nonetheless, there is a reconciliation at HERA energies. And then this basically motivated and ultimately allowed us to extract a low X and low scale gluon PDF using the effect approach, and I'll be using reweighting approach. And then I showed that they were consistent in the low X regime. So the upshot of all of this is that really we are in a position to finally use the exclusive JSI data in a global fitter framework. So we're sort of doing that internally by pushing things into XFitter. So it's sort of like a wee side project, but ultimately we want to emphasize to the global PDF groups that it'd be nice to include this exclusive JSI data into their fully fledged fitting machinery to really provide constraints on the gluon PDF at low X and low scale. So yes, that's all I wanted to say. Thanks a lot for listening.
Thank you very much. The recording.